Welcome to the 14th class meeting of the Introduction to DSP. Even though you took the midterm exam last night, again, homework. Okay. We are covering chapter 4 of the textbook, Sampling of Continuous Time Signals. And we've seen actually most of the things to be covered in chapter 4. The most important question is this one. So here is your C2D converter. And the input is a continuous time signal denoted by x sub c of t. And your output is denoted by x of n. And here goes the question. Let's say that the continuous time Fourier transform of the input is capital X sub c of j capital omega. And let's say the discrete time Fourier transform of the output signal as capital X of e to the j omega. Then find the output DTFT in terms of the input CTFT. And the sampling period, or equivalently sampling rate. So we want to answer to this question. And this is the first question. And second question is this one. So now you have the DT signal, x of n. Then can we have a system that may be called as a DT to CT converter, generating some x sub r of t. Here r means reconstructed. And the question is it possible for us to have this original signal back by using some system? Got it? Last time, this part is around, half done, and this part is also half done. We want to complete the last halves to understand these two questions. And the key is we understand what is going on in the C2D converter and the D2C converter, not only in the time domain, but also in the frequency domain. So you need to ask yourself, how can you describe the C2D converter's output in the time domain and frequency domain? And how can you describe the D2C converter's output in the time domain and in the frequency domain? Got it? So if you learned already, but don't remember, then stop and think. Got it? So here goes my another message. Always never hesitate to stop and think. Got it? It's a kind of strange era where a lot of video lectures available from the internet. The problem is that students just know how to fast forward or speed up the replay speed of the lecture, but they rarely stop, go back, and think. So please never forget that you have a freedom to stop and think. Okay, here goes the summary of last class meetings about sampling. So in the real world, we have a system called A to D converter, or analog to digital converter. Here, this is analog, that is digital. Got it? So this is a real world circuitry, a system. And this real world system is, of course, mathematically modeled in this course. Got it? As I repeatedly told you, what we do as an electrical engineer is to mathematically model something we want to build electrically or electronically or analyze electrically, electronically. Got it? So we introduce mathematical models. And these mathematical models may be there inside the real world A to D converter or not, depending on how you implement your system. As I told you, after using a mathematical model, you have abstractized, in Korean, 추상화. So you have abstractized already. And there could be many, many different, but mathematically same, except expressions to do those procedures. Sometimes you prefer this kind of mathematical description in your implementation. Sometimes that kind of mathematical expression to implement your system. So you will see at least one or two, at least two or more descriptions about C to D converter and D to C converter in this textbook. And they are mathematically same, but in some aspect, one way to describe it is easier to understand in some sense, and the other is much more easier and straightforward in some other application or understanding. So the key is that even though you know some mathematical operation, in a way, don't stop there and try to enumerate other ways, because some specific engineering problem can be easily solved by this point of view, but not that point of view, even though they are mathematically the same. Got it? Anyway, so here goes mathematical modeling of A to D converter. So we assume that inside the A to D converter, ADC or A/D sometimes. Let me just use ADC. We first have sampler or uniform sampler, and we have a quantizer or uniform scalar quantizer, and encoder or binary encoder. This capital letter ENC is usually used to mean encoding or encoder. Got it? So here goes the CT signal, and here goes the DT signal. And as I repeatedly told you, and some of you now sick of it, but for a most complete mathematical modeling of ADC, these three blocks need to be fully understood. The problem of this course, discrete time signal processing, even though our title of the course says digital signal processing, actually our textbook is entitled discrete time signal processing. We mostly focus on this part only. But I'm not saying that these are not important. These are also very important. However, we cannot cover everything about ADC converter or conversion in this course. This is an introductory course, so we mainly focus on this one. Got it? By the way, the real world analog and digital signals may have different definitions, but in our mathematical modeling, so this one actually could be something like this, right? Some continuous time signal but has special property. As I told you, this encoder may generate some non-return to zero signal. So it's a line encoder, it could be. In that case, output is actually an analog continuous time electrical signal, but having some 0 volts or 5 volts, something like that. However, when we study here, we model the output of ADC as a discrete time signal. Got it? So that is also very confusing, but we have to admit. Got it? So not only here, this is actually this is after quantization and encoding. So what can I say? This signal is actually XN. And okay, let me revise. So, yeah, let me say this. Okay. Actual ADC has continuous time signal having zeros or 5 or negative 2.5 and positive 2.5 approximately. But we model this as a discrete time signal. Then back here, we have a discrete time signal model. So we have interest in the relation between these two signals. Right? Okay, what else do I need to say? Yeah. So this one, this input, that output is called C2D converter. And C2D converter has a CT signal in and DT signal out. And in the time domain, what is the relation between the input and output? Output is simply the evaluation of the input signal at every integer multiple of t plus some possible offset. And this is sampling period or period. However, in most of the textbooks, they ignore this offset delta, setting 0 for convenience. So apparently, C2D converter has one input, one output, and one parameter. However, in practical world, you have to consider the offset. In the time domain, this block is easy to understand because output is simply the input evaluated at some integer times sampling period plus offset. However, in order to understand in the frequency domain, we convert this one into a strange two-stage representation. And what was that? So this two-stage representation is for a C2D converter. And we have what? Continuous time signal in. And here goes S of t, called the sampling function. And here goes x of s of t, another continuous time signal. That is, we may say, sampled signal. And here goes some strange box saying impulse to dt. Actually, modulated impulse train to discrete time signal, precisely speaking. Modulated impulse train to DT signal converter. And here goes x of n. So we have two subsystems serially interconnected inside a C2D converter. And one good thing to introduce this kind of intermediate signal, which is a continuous time signal, greatly enhances the understanding of these relations. And we will see. So let's try to find the CT Fourier transform of this sampled signal. And as we know that multiplication in time is equivalent to what? Convolution in frequency. And what is this one? What we know from the signal gen systems is that this S of t, which is the impulse train with period capital T, has the CT Fourier transform again the, what is that? I believe, and something like this. Got it? So if I plot these two impulses, here goes the time axis, here goes the radian frequency axis, and delta functions has spacing capital T, and here the delta functions has spacing 2 pi over capital T. Got it? So if your sampling function has very short period, then these delta functions have wider and wider spacing because they are reciprocals inside the arguments of the delta function. So if you plug in this one here, then 1 over 2 pi and 1 over 2 pi cancels. And if I remember correctly, is it correct? Just a second. I believe so. Yeah. We have xc j omega convert with summation of delta functions. And from the shifting property, we have this relation. Got it? I hope I'm correct. Yeah. Let me check because sometimes that coefficient is very, very confusing. So yeah, I believe I'm right. Here, the capital omega sub s is this one. So this is sampling rate in radians per second. Got it? So far so good. We have found the relation between the CTFT of this input signal and the CTFT. Be careful, the CTFT of this continuous time signal. And in the last class meeting, we didn't cover how to obtain the DTFT of the output of C2D converter from that one. Not yet. So we are going to cover that today. But before we do that, in the last class meeting, we little bit were exposed to the second problem. So here, in the second problem, we wanted to reconstruct the signal, continuous time signal, as close as possible to the original signal by using the C2D converter output. However, since in the first problem we didn't talk about that one, so in the second problem we considered a similar problem, such as from this signal, right? From this signal, how can we reconstruct that signal? Got it? From this signal, how can we reconstruct that signal? So this is the entire story. And you may say that, okay, professor, I got it. You repeat the same thing again and again. Why do I do that? Because when I was an undergraduate student, this type of description was so confusing. I still remember my pain 30 years ago. So that's why I'm kind of giving you the big picture of how the authors of our textbook have written this part. Right? So we have drawn some figure, such as, okay, for convenience, let's assume that the CTFT of the input signal, the signal to be sampled, is a triangular function. And here goes the CTFT of the sampling function. Then what happens? As you know, this centered delta function convert with this one, copies that one and places here. And the first right side one moves this to the right side. This one moves to the right side by this amount. This one moves the spectrum to the left side, blah, blah, blah. So what will happen? This one will be copied here, and there, and there, and so on, and here, there, something like that. And suppose you do not know the original signal, the continuous time signal spectrum as a triangular function, but you are just given the CTFT of that signal. Now, can you guess without hesitation that the original signal was this one? And actually, no. Why? Because from here to there could be many, many options. For example, this could be one option. Right? So when you add them up, you have triangle, flat, triangle, flat, triangle, flat. So I have given you this triangle, flat, and band limited signal. Suppose these two are converged. The Sj omega and this one is converged. Then you have the same spectrum. Ready? Do you understand what I mean? So from the spectrum of the sampled signal, sometimes, not always, sometimes you are not sure what was the spectrum of the original signal, as this shows. But as you see that two different input spectrum generate the same output spectrum, right? So there is no uniqueness of the input signal is not guaranteed in general. Got it? However, if you assume the input signal satisfies a certain condition, then the uniqueness is guaranteed. What is that one? And as you learned in signal gen systems or in the last class meeting, this is one condition and actually the unique condition. So suppose the signal is band limited, strictly band limited. What does that mean? Strictly band limited is that if you draw a Fourier transform, after some cutoff frequencies, we usually take plus and minus capital omega sub c, then there is the CTFT is zero valued. Got it? And second condition is that your sampling rate is greater than twice the maximum frequency content, so that you have something like this. So when you multiply the sampling function in the time domain, in the frequency domain, no overlapping of the replicas occur. That is the condition. And we will see more about this one. Got it? So for perfect reconstruction, we haven't yet defined, but I'm going to. We need strictly band-limited signal, and sampling rate satisfies blah, blah, blah. But here was something strange, and this is what I want to say. In one of the last previous class meetings, I classified the continuous time signals. The one is that absolutely integrable and square integrable. Similarly, DT signals as absolutely summable and square summable signals, right? And square summable signals, square summable DT signals, or square integrable CT signals have a very nice property. What was that? The Fourier transform, actually Fourier Plancherel transform, always exists. And inverse transform also exists. And you've seen from Parseval's relation that the energy of a square integrable or summable signal has what? Its counterpart of the representation of the energy. What was that? Integration or summation of the magnitude scale of the Fourier transform, right? So in perfect, when we talk about perfect reconstruction, this finite energy condition is actually very, very important. But professors do not want to talk too much about this square integrability or summability because it's over the scope of the undergraduate signal gen systems and DSP, or they do not know. Got it? So that's the problem. So we just say, and a tragedy occurred to me when I got PhD and searching for a job in the United States as a faculty member of a department. And let me tell you what happened. So if you get a PhD and if you apply a tenure track faculty position in the US universities, they usually invite you to come to their university and provide an open lecture. And usually not only professors, but also undergraduate students comes and evaluate, even some university evaluate your talk. And you have not only the lecture, but also Q&A. The problem is that when I was invited to do the faculty position talk, one of the professor in one of the department asked me, saying that, suppose you have sine function. It is sampled at every 1 second. And if you evaluate, then what happens? Your output is 0 for DT signal. You have a sine function, and this is 1 period, right? But you know from the Fourier transform theory that you have 2 direct delta functions. Actually, one is negative. But anyway, yeah, something like this, because sine is from the Euler's formula. You must be very good at converting sine and cosine using complex sinusoidal signals. Got it? Anyway, so let me ask you, is this signal strictly band limited or not? It's strictly band limited. Why? Because if you choose some cutoff frequency greater than 2 pi, then what do you have? Outside the band, you have zero signal, right? So in that sense, your sine function is strictly band limited. Now, you sample at this rate. Is it? Am I correct? I'm sorry. Probably the original question was this one. And yep, this one. Still no problem, right? Got it? And sampling rate is here, 2 pi, negative 2 pi. So maximum frequency content is less than the sampling rate, right? What's wrong? The sampling rate is twice the maximum frequency content. The signal is strictly band limited. Why you cannot get this signal back from this signal? It's obvious because it's all zero signal, and how can you get some non-all zero signal, right? And at that time, I realized that the professor who asked the question dig a hole for me to fall in. Okay. Anyway, I murmured, oh, well. And interestingly, I had 6 interviews. So I interviewed 6 universities. And I got 5 offers, except that department. Got it? Yeah. Probably this was the problem. And now I know what happened. The first thing is that sine function is not a finite energy signal. It's an infinite energy signal, theoretically, right? Right? And second one is that, well, no finite energy signal has direct delta functions in the frequency domain. So this type of thing, the sampling, half of the sampling rate has some delta function there. This kind of thing never happens for finite energy signal. Got it? The problem of this sine function is anyway because it is not a finite energy signal. And then why finite energy signal is so important? Because even though most of the textbooks don't explain for the theorization of the sampling theorem, they actually use Fourier Plancherel transform, which is applicable to square integrable signals. What does that mean? Finite energy signals. Got it? Anyway, in order to have a more in-depth understanding, I recommend you to first go to the math department and take introductory analysis or real analysis course, 해석학. And then if it is enough, then go to the library and take out Fourier analysis books. There are tons of books, more than 200, I believe, and read them. And if you feel that you are not yet ready to read those books, and take the math, go to the math department, take another course called Measure Theory, 측도론, and then you may be better prepared. Got it? So that is the trouble. Anyway, so let's see the lecture note, which has a lot of figures from the textbook. So this page repeated again is like this. Suppose your original signal, this one, is strictly band limited with maximum frequency content, capital omega sub capital N. Here, N means not the number, it is for Nyquist. Got it? By the way, Nyquist is a person's last name who is kind of dedicated to the discoverer of this theorem. And as you see that if this impulse train or sampling function in the frequency domain has larger spacing than twice of this one, then you have something like this. So here you have omega sub n, here you have omega sub s, then you subtract what? Omega sub n, and these two must be what? Omega sub n must be less than omega sub s minus omega sub n. So you have a condition like this. Ready? So in order to have no aliasing, which alias means, what is alias? Alias has the common root with alien. Is it en? Or alienate? Something like that. So in Korean, sometimes alias means 별명, sometimes 타인, 외계인, and sometimes 소원해지게 하다, something like that. Anyway, so another name or something. And this aliasing occurs, if aliasing occurs in the sampling procedure, you have something there shouldn't be, like some monster alien. Got it? Anyway, we just say aliasing occurs if this condition is violated, but in the frequency domain, overlap of replicas of the spectrum occurs if this condition is violated. And we don't want that because we want to do some magic. What kind of magic? We have uncountably infinite pairs of t and the value of the continuous time function. So uncountably infinite pairs. But somehow we want to just take countably infinite number of pairs. And we want there exists a way to reconstruct that signal from these pairs. And it seems it's impossible. However, under certain conditions, it's possible. And this is the condition. Ready? Signal must be a finite energy signal, strictly band limited, and its maximum frequency content multiplied by 2 must be less than or equal to, because there is no direct delta, to the sampling frequency. That is the discovery. And what is this one? This one is more amazing. So we've seen this part, and this is for reconstruction. As I told you, we want to answer to 2 questions, but before we answer 2 questions, we kind of intercept an intermediate signal, x sub s of t, and then consider frequency domain relation and perfect reconstruction. That's what I told you. And as you see that from here, because this is the spectrum of this signal, if we have a strictly band limited frequency response with proper scaling like this, so we put an ideal low-pass filter like that, and we scale by t, then we have the original signal back. So the Nyquist condition, what is that? Strictly band limited finite energy, and sampling rate is greater than or equal to twice the maximum frequency content. That is what? That enables perfect reconstruction from uniform samples. Be careful. Sometimes we forget about these two. Think about this. Suppose you have a finite energy signal and you sample uniformly, then how many samples mathematically? Countably infinite samples you need to keep for reconstruction. But in reality, what do? We usually discard infinitely many and keep finitely many, right? Finite, 100 samples, 1 million samples. Then perfect reconstruction is possible. It depends, right? As I told you, in real world, we always handle finite number of samples. What is infinite? Infinite means, in engineering sense, sufficiently large amount of samples. So be careful. Sometimes this using just the finite number of samples, sampled fast enough and number of samples large enough, is in practice, in engineering sense, enough for perfect reconstruction. But theoretically, it's not possible. Got it? Anyway, we will see, and you will see from some homework problems or final exam problems why you cannot have perfect reconstruction if you take only finite number of these pairs. Got it? In general, you lose some information by taking only finite number of samples. Anyway, so here, aliasing is not yet well defined, but anyway, we understand it as some unwanted overlapping of replicas of the shifted versions of the original spectrum in the frequency domain. And let's see what happens using some examples. So here is an example. Suppose you have a tone signal. By the way, what is a pure tone or tone signal? It's like sinusoidal signal. And probably from some AM radio broadcasting, you've seen so-called chime signal, like such as Shibo, something like, okay, we will announce it's 7 p.m. B, something like that. That B signal is actually a pure tone with different frequencies depending on which broadcast systems you listen to. So here goes a pure tone. And you have radiant frequency omega sub 0. So in the frequency domain, you have two direct deltas located at plus and minus capital omega sub 0. And this signal is to be sampled faster than twice the maximum frequency content. And the authors have chosen cosine and have chosen the sampling rate greater than twice the maximum frequency content. But as I told you, something bad happens if you put equality here. Okay? And as I told you, the theorem does not apply to this signal actually, because it's an infinite energy signal. That's why the authors wanted to circumvent that trouble by not putting here the equality. Got it? Anyway, so suppose your, where is your sampling signal? Yeah, just a second. Oh, this is sampled signal, right? So here goes your sampling signal. And now you convolve, then what will happen? Now, this part will be copied and shifted and pasted at the sampled signal's Fourier transform. So you have one replica and you shift it and shift it, something like that. So your sampled signal will have these many delta functions. And can you recover the original signal by using a low-pass filter? Yes. As the authors kindly put here as a rectangle, if this is the ideal low-pass filter's response, then what would be the Fourier transform, CT Fourier transform of this one? Since this is ideal low-pass filter, these are gone. And if the height is properly scaled, so T and I believe 1 over T, then you have your original spectrum back. So you may say that, hey, the output is a perfect reconstruction of the input. So far, no aliasing, no something unwanted is coming. None your friend is coming. Now, here goes another story. Suppose your sampling rate does not satisfy the Nyquist condition. Then what happens? Let me see. Yeah. So this figure is something strange, but let me plot. So yeah, this one corresponds to that one. Got it? So this does not scale. It's a kind of magnified version. Got it? And that one is here. Got it? Now you copy this one here. Then what happens? This one appears there. Now you copy this one here. And this one, copy of that one appears here. Right? And if your low-pass filter happen to cut out these things, what will happen? These tones has frequency less than omega 0. So suddenly, this reconstructed signal has something like this. So originally, the signal was tone like do. Suddenly, you have do. So new frequency component appears at the output. Originally, there was none. By the way, let me repeat. This figure is very, very misleading because as you see that this one is located at negative omega 0. Got it? So if I were the authors, I would not have drawn this way, but anyway. So aliasing in the frequency domain introduces some frequency component originally was not there. Got it? Anyway, so here goes the summary of Nyquist sampling theorem. And suddenly you may wonder why this guy's name is here, Shannon. Sometimes this theorem is called by many people Shannon-Nyquist theorem, but actually this is not correct. Okay. Nyquist sampling theorem is for finite energy deterministic signal. And Shannon extended Nyquist theorem for finite, so strictly band-limited, finite power random process. And after combining these two theorems, people call the theorem as Shannon-Nyquist sampling theorem or Nyquist-Shannon sampling theorem. So according to our approach, where we only consider a finite energy deterministic signal, or without proving, sometimes we just introduce delta functions to handle some important non-finite energy signals in sampling theorem. But still, we only consider a deterministic signal here. And as you learned in 전자수학 A or the probability in random processes. After you learn about random processes, then the sampling of random processes, strictly band limited, finite power, is related to Shannon's sampling theory. Got it? So just cross this part out. Okay, not here. What is this? Just a okay. Anyway, so maximum frequency content of the input signal is called the Nyquist frequency, and twice the maximum frequency content is called the Nyquist sampling frequency or Nyquist sampling rate. Got it? Anyway, now here goes the final parts, the last half parts of the first question and the second question. So far, in the first question, we studied what's the relation between the CT Fourier transforms between this signal and that signal. But we want to relate the DT Fourier transform of the output of C2D converter with the input CTFT. Well, here comes some strange block saying impulse train to discrete time sequence. But I prefer to saying that modulated impulse train to a DT signal. Ready? Because impulse train usually means equal height impulse train. But if the height varies, then something changing means modulated. Got it? So in order to find the DT Fourier transform, let's use the definition of the DT Fourier transform. What is that? X of n, we inner product with complex sinusoidal signal. And here, what are the variables? N's. So we have n. This is the definition of DT Fourier transform, and conjugation of complex sinusoidal signal is just e to the negative j omega. This is why we have, in sum end of the summation, we have the product between the original signal and e to the negative j omega n signal. Now, what was this one? CT Fourier transform. And what is this one, by the way? This is simply e to the negative j omega t dt by definition, right? Now, we know that this signal is what? Is summation of x and t delta of t minus nt. And here, again, we boldly change the order between the infinite sum and integral. This is not allowed actually, but we just say that it's okay in engineering sense. Got it? Because in engineering sense, these infinities are actually some very large finite numbers. And if they are really finite, then interchange the order doesn't matter. So we have this one and that one. And we have the integrals. Am I right? Now, we eventually, we eventually have something amazing. What is this one? Let's compare this one with that one. And we want to rewrite this one using this one. If you compare these two, what's the difference? Instead of lowercase omega, we have capital omega, capital T. Right? So this is the relation. Got it? Isn't it amazing? Now, in math, what does this mean? Suppose you have input, not input, the sampled signal to Fourier transform. You know what it is, right? You have infinite replica of the original signal to be sampled with repetition period that is what? Integer multiple of sampling frequency, right? So this one, well, there should be some figure. No, okay. Let me draw. So you have something like this. Am I right? We assume that the Nyquist condition is met. Of course, this theorem, this result applies when aliasing also occurs. Now, what's the meaning of replacing capital omega with lowercase omega over t and draw a function as a function of lowercase omega? What does that mean? So as you already know how to do this, because this kind of problem occurred again and again and again in your middle school exams, as I remember. Let's plug in this one here. Then what is omega s? That is omega s over t, right? Am I right? Just a second. No, right? Because here, what was capital omega sub s? It was 2 pi over t. So actually, this is nothing more than 2 pi. And what is this one? 4 pi. 2 pi, 0. So suddenly, what do you have? You have a function that is periodic with period 2 pi. And as we all know that DT Fourier transform over discrete time signal must be periodic with period 2 pi if we use radian frequency, lowercase omega. And now in our sampling, especially C2D conversion, what happened? In the intermediate signal, you have repetition and your repetition of the replica by sampling frequency. Now, if you convert that one to a discrete time signal, this sampling period becomes always 2 pi. So actually, from here to there, if you just take a look at the output DTFT, you lose one information. What information? Sampling frequency. Because every sampled signals, DTFT, shows period with period 2 pi, not the original sampling frequency. This is very confusing and will occur again and again, and you will see in some homework problems. And you must remember this one. Got it? So here, you have repetition at every integer multiple omega s. And here you have repetition at every integer multiple of 2 pi. Got it? Now, we are almost done. I will skip this part. You read it. There it is. Let me. Yeah. So let's see the second half part of the second problem. What was the second problem? The second problem was like this. Suppose you have a discrete time signal, and here goes D to C converter that generates some reconstructed signal. And now, how can you describe this two-signal relation? We know how to reconstruct the signal from this signal, right? So what do we do? Here we have something like this, right? So ideal low-pass filtering gives us the original signal back. We know that. But we do not know yet about what is the mathematical description relation between these two and what's going on. We only know here the relation between these two in the frequency domain. So let's see more carefully, okay? Now, we start from the idea that this signal is continuous time, and that signal is also continuous time. And this is an LTI system, CT-LTI system. An ideal low-pass filter is a CT-LTI system. Then it has some impulse response h of t. So actually, output is the convolution between these two, right? And what is x of s of t? As we've just seen, this is what? So this representation of the sampled signal occurs again and again and again and again. That's why the authors of our textbook loved this two-stage representation of C to D converter, even though that gives a lot of confusion. Now, anybody? Sigma n from negative infinity to positive infinity, x of C of nt times what? H of t minus nt. Why? Because this convolution applies only to time functions. So you can take this sigma n constant, not a function of t, here, and convolve h of t with delta of t minus nt, which just shifts h of t. That is here. Now, you may say that, okay, so what? And what is the impulse response of the ideal low-pass filter with t omega c equals, for example, omega s. Half of omega s. Cutoff is just half to avoid any problem. In that case, in this case, amazingly, we have here sinc function like this. Am I correct? No, not correct. I need to scale it. Just a second. Is it 1 over t? Yeah, I believe so. Yeah. Yeah, I believe it's correct. Where sinc t is defined as sine pi t over pi t for t non-zero and 1 for t 0. So sinc of t crosses x-axis at every integer except the origin. And now you have this scaling. So what happens? Sinc t over capital T crosses the x-axis every integer multiple of t. So what happened? What happens? In this operation of modulated impulse train to a continuous time signal reconstruction, actually what we do is what? We use sinc functions with crossing rate 1 over capital T. It happens to be the same as the inverse of the sampling rate. And we shift and we scale the sinc function and shift and sum up. What will happen? So this is what's going on. So suppose this is 0 and this height is x of 0, x of c 0 t. So x of c of 0. And here at t, you have xc 1 times t. Here, xc 2 times t, blah, blah, blah. Now, the reconstructed signal, xr of t, is what? First, you have the first term, 0th term, that is scaled version of sinc function by the continuous time input signal sampled at 0. Now, what is the first term? N equals 1. You have this one, right? So you have shifted sinc pulse by capital T and scaled by the first sample. And you do this procedure countably infinite times for all n, and then you sum up. Then what will happen? These signals, a lot of signals overlap, and you have some smooth function, right? And if the Nyquist condition is met in the sampling and in the choice of the cutoff frequency of your ideal low-pass filter, what will happen? This signal reconstructed by this procedure gives you the original signal back. Got it? And you may still say that, oh, well, what about the complete picture of the C to D2C converter? So D2C converter can be viewed as a two-stage representation again. So here, this one, DT to modulated impulse train. So actually, you reverse what occurred in the C2D converter in two-stage representation. So you have XS of t. Theoretically, you don't do this in reality. And here goes what? Here goes ideal low-pass filter. Then you have perfect reconstruction if some certain condition is met. Or if you just want what? Mathematically, just you do this operation. Done. Got it? So this is what's going on in the D2C converter. Sometimes this point of view directly generate the continuous time signal by multiplying each sample, each term of the DT signal with delayed or advanced sinc pulses and sum up. Sometimes you view the D2C converters inside as what? First, you have a discrete time signal to a modulated impulse train. So what is this one? This one is x of n delta of t minus nt. And then you have low pass filter. Continuous time signal in, continuous time signal out, low pass filter. They are the same. Got it? So you have the entire picture. So this is what I have drawn. And ideal C2D converter in frequency domain. And as I told you, you have sinc pulses, blah, blah, blah. And in practice, we never have this one. We can never have impulse train, not alone impulse, modulated impulse train. Then what do we do? Actually, the circuit guys, circuit engineers, have noticed that, hey, Professor Cho, in real world, we are not handling a sequence. We are handling what? A continuous time signal that has something. So what they do is they design so-called sample and hold circuit. So it's like, even though they in real world, they handle continuous time signal, let's just believe it's well modeled as a discrete time signal. Then what's going on here? Here, you have something like this. And it's very similar to the previous one, except that you have a rectangular pulse. But actually, if you plot this one, what you will see is something like this. Something like this. Got it? So it's same as, mathematically speaking, same as the system C2D, a D2C converter that does not use a sinc pulse, but use a rectangular pulse. Got it? So mathematically, we can think about a D2C converter, non-ideal D2C converter, utilizing a rectangular pulse with width same as the sampling period. And you may say that, okay, but Professor, this figure is different from this one. So if we have used sample and hold, then what would be the output? Something like this. Right? Some stairway type thing, right? Piecewise constant function. That is not the original signal. But interesting thing is that we may compensate this sample and hold circuit with another filter. So this is kind of correction filter. And we may make the output almost the same as what we wanted. Anybody? Anybody has idea about this filter? Think in the frequency domain. So this is what? This is actually can be viewed as what? This can be viewed as, I'm talking too much. You can view this as what? Again, DT2 modulated impulse. And here, this one has impulse response rectangular pulse. Now you have some H2, and you want this entire serial cascaded signal, convolved signal, to be a sinc pulse. So actually in the frequency domain, what you need is this one. Or in the time domain, so you somehow design this correction filter, LTI system, so that the sample and hold followed by this correction filter works as what? As a almost ideal low-pass filter. That is the idea. And this problem occurred twice in the introduction to DSP when I was taking the undergraduate course. So this problem appeared in the second midterm. At that time, we had 2 midterms. Second midterm exam. The problem was difficult. I lost it. I couldn't get the full credit. So I studied carefully because the professor spread the problem set. I studied carefully. Not many my classmates studied that again. They said, okay, let them go. Okay. And professor just copied exact problem, the same problem in the final exam, and put larger points. That is what happened. And I got it, fortunately. Yeah. Many of my classmates lost it because they didn't took a look at carefully. Okay. This is very important. Just draw in the frequency domain, and what will happen? You have this one is what? In the frequency domain, it's a sinc pulse. And this one needs to invert this part and need ideal something. So what I remember correctly is that this correction filter has frequency response, something like inverse sinc with brick wall fall-off, something like that, with proper scaling. Since I explained this part carefully and still remembers that feeling when I was taking this course, you may expect that will appear in the final exam. And if I believe I still have that problem set when I was taking 30 years ago the final exam. So if I have it, I will photocopy and put it in your final exam so that you see the exact problem. Okay, anyway, in practice, sample and hold filtered by some filter to best approximate sinc function interpolation. By the way, this operation or that operation is called interpolation. And actually, this is uniform interpolation or periodic interpolation. And anyway, so we are done with actually section 4.3. All the rest of part I didn't cover. You can read it. But about this part, practical example of communication signal, you may skip it. I will not ask you this one here in this introduction to DSP course. It may be too much for you. But this part is related to what you've seen in one of the MATLAB homework problem. So please read that and find the differences. Okay, that's all for today.